All right, we're going to look some more at our frames and machines. We did a little introduction last time. So I thought today we would go in and do a couple of more examples. So probably two examples of frames and machines that have a couple of new features to them. Some that we haven't seen before, some that we haven't really used yet. I think we'd start with this one. So this is going to be our frame. And I guess I realized that I didn't draw. This is a roller rolling on some kind of surface up here. We're going to have this guy pinned to the ground, and we're going to put some forces on here. Let's see if I can find a force. We're going to put a force over here. So when a couple of things about just this make it not a truss, right? So first of all, we have some parts that aren't triangulated here. These are just kind of cantilevered or sticking out here. This is all one piece across the top. So it's not a piece that ends here and a piece that ends here. It's all one long piece. Same thing for this. So they couldn't be truss pieces because this one has 1, 2, 3 connections on it. And so does this one have 1, 2, 3 connections on it. So neither of those could be truss pieces. And it's not triangulated. And then we're going to put a force on here on the side, which we can't do with trusses. We can only put forces on trusses at the joints. So when I put the force on the body of the member itself, then that also creates a problem as far as trusses go. I don't have a nice little 3D printed version, but we're going to put a distributed load kind of all the way across the top of this thing here. And it's going to be evenly distributed. I'm just going to draw it in. And something like this. So we have a evenly distributed load across the top of the frame. We can tell it's a frame and not a machine because of our pieces. We have 3 pieces, 1, 2, 3. They aren't configured in a way where they can move relative to one another. So if they could, if there was a hinge point somewhere where one of these pieces could rotate and the others could not rotate or whatever, then it would be a machine. We'd still work it the same way, only a lot of times with the machines, they're not necessarily bolted down, or we can't find that external reaction first. Not 100% true, but often it's true. Like if they were pliers or something like that, they wouldn't be bolted down. Some machines are bolted down. So this is our setup. This is our frame. And we need to go in and we're going to have to label, dimension, all that kind of stuff. I'm going to end up drawing this, so this is just here temporarily. First of all, we need to go in and figure out these reactions, right? We have 2 reactions at this pin and 1 reaction at this roller. And I think now would be a good time to take the pin and the roller, take them off of the truss, not the truss, the frame, and replace them with the reactions at those locations. So I'm going to try and get the pin off of there. We had a pin. We're going to replace it with a, we'll call this point here at the center, that'll be A. So this will be AY, and we'll have AX over here. We don't know either of those. We're just putting them in the X and Y direction. Same thing for the roller up here. Let's get it out of the way. Now, remember, roller only has 1 reaction. As long as it's a frictionless roller, which is what we're assuming we're dealing with here, then get it straight again. Then the reaction is perpendicular to whatever surface this roller was gliding along. It's going this way. So the reaction is perpendicular to that. This would be A, B, C, D, E. This would be E up here. So let's put EY. So it's disconnected from the world. Now it's a free body because it's not connected at the pin, not connected to the roller, and we've replaced those connections with forces, so it's just a free body now. And let's go ahead and replace our, our plastic piece with a force here. Let's make that force, I think, let's make it 1700 newtons. Let's go ahead and get some dimensions on here. let's say this distance, these little pieces, let's make them 300 millimeters. So 0.3 meters. Let's put this force kind of in the center of this span, but this is a larger span than that one. Let's make this one 400. So this will be 0.2 meters, and this will be 0.2 meters. Let's draw our other dimensions that we need. Let's put them up here, I guess. No, let's leave room up there for our distributed load to be worked on. So let's pull them all down. I'll use a ruler to try and get them kind of straight. And then one over here. It may not be perfect, but they'll be kind of straight anyway. All right. Guess I was drawing arrowheads, wasn't I? This one actually needs to go to that point. When we move this, I'll pull it over there. These are the same. This is the same distance as that. So let's make these 0.3 meters. Okay. Let's mark the center of all of our. I already marked those. There's one center. There's one. There's one. And let's draw in our frame here the way we had it. So this piece, A, this will be B, and let's put C there. This ABC, this was all one piece. I'll actually try and draw it neatly. So something like that. C, this is D. E is all one piece. Kind of draw it somewhere around here. And then we had BD connecting these two together. Something like that. So I think we've got a good free body diagram now. It's always good for when you're working with a frame and machine to look and see if any of these pieces are two force members, because that will help you out in the long run. Generally with frames and machines, it's kind of like finding zero force members if you're working with a truss. So these pieces ABC, just the fact that it has a name ABC means it has 3 connection points on it probably. So it is not a two force member because it has 3 connection points. CDE has 3 connection points, so it is not a 2-force member. BD has 2 connection points, and it has no force applied to the member directly. You know, there's no force applied here. So BD actually is a 2-force member. So that's usually good to know. And let's just highlight it so that we don't forget. All right. So there's our 2-force member. So I think other than this distributed load, it needs a value. Let's make it 2,000 newtons per meter. And it's spread over 0.6 meters, right? So it goes from here to here to here, which is a total of 0.6 meters. So let's see. 2,000 newtons per meter times 0.6 meters is 1,200 newtons. So this distributed load can be lumped into a single point load of 1,200 newtons. And we put this point load at the centroid of this distributed load. So this is evenly distributed. Basically, it's a rectangle. So it will be at the very center. I'm going to draw in a arrow here. I'm using a different color to kind of remind me that this isn't regular external force. This is the lumped version of this distributed load. And it was 1,200 newtons. And it does line up right at point D, although it doesn't have to. You know, if these were different dimensions or whatever, it's the 1,200 newtons lines up at the centroid of this distributed load. So now I think we're good as far as the free body diagram goes. So what we're trying to do here. Probably the first step, if you're working this as a exam problem or an academic problem of some type, then probably this problem is asking you something about the force in member BD. That's probably a typical thing that this might ask. Or maybe it's asking you to find all the forces at every pin, something like that. Either of those generally start with finding some or all of these external reactions before you start taking the truss apart. Not the truss, the frame apart. So why don't we do that? Let's get some blank paper. Leave that down here and get us a blank sheet and write some equations. So we've got a free body diagram. And generally what I'm going to do when I'm working on finding external reactions is find the two that are at the same point. There usually are two. There may not always be, but in classes like this, there's generally two at one point. And that point is usually where the pin was, right? So there was a pin right here. We replaced it with these two unknowns. So I'm going to find that point and do summation of moments about that point. So in other words, I'm saying that the whole free body here should not be rotating about this point. So it shouldn't be, spinning around about point A. But for that to be true, the summation of moments about point A has to equal 0. So that's the equation I'm going to write. I want to choose a direction to be positive for my rotation. I'll say clockwise is positive. And then I go and find all the forces that are trying to make this free body rotate about point A, and I calculate the summation of their moments. So AX and AY, AY and AX, their lines of actions actually go through point A, so they're not trying to rotate this body about point A. The 1700 newtons here is, it's trying to make it go around clockwise. The 1200 newtons is also trying to make it go around clockwise. EY, if I push up at EY, then it would try to go around counterclockwise. So these two get a clockwise sense, and this one gets a counterclockwise sense. So the 1700 newtons here, I said clockwise is positive, so that's a positive 1700 newtons. It is a horizontal force, so I need the vertical line of action, or the vertical distance between 1700 newton line of action and point A, where I'm summing moments. So that is 0.3 plus 0.2, 0.5 meters. So the distance between this line of action for the 1700 newtons and point A is 0.5 meters. So we'd say it has a 0.5 meter moment arm. The 1200 newtons, also clockwise, and it is a vertical force, vertical line of action. So I need the horizontal distance between point A and that line of action. So that's 0.3 meters. So 1200 newtons with a 0.3 meter moment arm. EY, also vertical line of action, but counterclockwise sense, so minus according to my equation. And its moment arm is 0.6 meters. From this line of action to point A, the perpendicular distance is 0.6 meters. So we can solve this equation. There's only one unknown. So 1700 times 0.5, this is 850 Newton meters, plus 1200 times 0.3, 360 Newton meters, minus EY times 0.6 meters. All of those equal 0, so I'll move the minus EY to the other side. It becomes positive, and I get that EY equals 850 plus 360 divided by the 0.6 coefficient with EY. 2016.7. And that's just newtons. It came out positive, so we did draw the arrow for EY in the right orientation. So we don't have to worry about doing that one backwards or something. At this point, I'm interested in figuring out AX and AY. At this point in a problem, if I'm solving a problem, I might be done with the external reactions. Maybe I take this EY and draw this free body diagram and start working on the individual pieces. But we're going to do the whole thing, all the little pieces. Then, but if you're trying to, make this more efficient, you're trying to solve it for an exam or something like that, then you probably just need EY and that free body diagram. But we're going to go and solve forces in X and Y to get these values. So let's do X. So in the X direction, I have AX is unknown, but it's going to the right, so that's plus AX. I have plus 1700 newtons from this external force. None of these forces over here have external forces in the X direction, so they don't go into this equation. So it's just 1700 newtons plus AX equals 0. So therefore, AX, turns out I drew it the wrong way, so equals negative 1700 newtons. And then I'll do the same thing for AY. I've got AY is a positive, by the way I drew it anyway. I've got a total of 1200 newtons pushing downward. This is from the distributed load here. So minus 1200 plus EY. So summation forces in the Y direction equals 0. I have AY minus 1200 newtons from the distributed load plus, and I'm going to write EY, and then I'm going to take the value of EY that I calculated and plug it in there. I generally like to do it that way in case I don't want to lose a negative sign somewhere or something. So this equation would then be 0 equals AY minus 1200 newtons plus 2016.7 newtons. AY goes to the other side of the equal sign, and I end up with, therefore, AY is equal to, it becomes negative. This term is positive, so it's actually a negative 2016, which is still in the calculator, minus 1200, 816.7. So actually AY should have been pointing downwards, apparently. That sort of makes sense. If I'm kind of pushing over here, this thing might want to lift up, so maybe this is pulling it back down and pulling downwards on to hold it in place. But let's make sure that we actually calculated it right. So let's see. Minus 1200 plus EY. Looks like we did that correct. All right. We'll go with that. I think it's correct. Now we've got our external reactions. Both of these calculated that they were in the wrong direction. This one certainly is in the wrong direction, and this one seems to be in the wrong direction, although I want to make sure because we don't want to get too far and then have to undo anything. So let's just check. AY minus 1200 newtons plus EY. EY is a 2000 Newton force, unless I copied that one down wrong when I know it's still in there. So that looks right. 850 plus 360 divided by 0.6 is the 2000. So that term is positive. Then that becomes negative. So I think we're right. Negative. You just always want to check those because you don't want to get off into the the details of an individual piece of the frame and then realize that you did one of the external reactions wrong. All right, so we have our external reactions. We have AY or EY, AX, and AY. The next step would be go back to here and pick one of your free body diagrams for an individual piece of the frame. Now we're going to do all of them, but you would pick one of them and kind of unbolt, imagine that these are bolts or whatever, and unbolt it and take that piece out and draw its free body diagram. And it doesn't particularly matter which one you do, although if you did the two-force member and you took that piece out, it wouldn't give you any new information. It would just say that the force in the two-force member equals the force in the two-force member. So you really need one that has some known values applied to it so that you can actually calculate something. So the better ones would be ABC or CDE, one of those two. Let's do ABC. So we've got, try to get things straight here. There's our member ABC. Now we need to put the forces on it. So we have 1700 newtons in this area. We have C. C was originally the pin that holds the top piece to the vertical piece. So neither of those are two force members. So at C, what we have to do is just write pin reactions, which are CX and CY. Now, they don't have to be horizontal and vertical. There can be some situations where it's more convenient to write these at some angle, maybe line up the X with whatever axis the piece itself has, along that longitudinal axis. Sometimes that's convenient. In this case, the longitudinal axis for this is vertical, so I lined up CY with that. At B, we did have a two-force member. So instead of writing the normal BX and BY pin reactions, we can write this. The force in member B, and the other end of this is D. And it's at some angle. The line of action for a two-force member is along a line that connects the two pins for that member. So we don't necessarily know which way to draw it, but we know it's on that line. So I drew it this way, up and to the right. And we know what angle it's at based on the geometry, because we have a run of 0.3 millimeters and a rise from D to B of 0.4 millimeters. So we know that this is a 3, 4, 5, so a 0.3, a 0.4, a 0.5, it doesn't matter, the ratio is the same. 3, 4, 5 triangle that describes that. Or you can go in and calculate the angle theta and use that directly if you want to. I'm going to use this rise over run. At A, we have our external reactions from the pin that was A, from this guy that's holding the frame steady. We just calculated those over here and we got these negative numbers. So what I'm going to do is I'm going to draw the correct orientation on the free body diagram for ABC. So AY apparently should go down 816 and AX should go to the left 1700. And this was 816.7 newtons. All right, so there's our free body diagram for ABC. We should probably put our dimensions on there so that we, actually let's do this first. So we'll need to know that one. I don't like it. There we go. And that one. And we'll do this. This was, I think I made it 2. Oh, it's right here. 0.2, 0.2, and 0.3 meters. And these are all meters. I'm just going to leave them off to not get too cluttery right here. All right. So at this point, we have a free body diagram with three unknowns, 1, 2, 3, and since it's a non-concurrent force system, it's clearly there's one common point over here, there's a point, there's some point, there's all kinds of intersection points here. It's not concurrent. So that means we have three equilibrium equations for it: summation of forces in x, y, and summation of moments. So we have three unknowns, three equations. We should be able to solve for all of these. If you didn't see this was a two-force member, then when you drew this force, you would have drawn bx and by, like we did here at C, and you would have 1, 2, 3, 4 unknowns and only three equations to work with. So at that point, you might could have solved some of them, but you couldn't have solved all of them. I think you could have basically gotten the cx and bx, but not the y. So what you would have done then is you would have drawn CDE, generated a couple of new equations, three new equations with it, but only actually no new variables because CX and CY are over here. And well, maybe you would put DX and DY over here. I don't know how you would have done that. If you didn't know it was a two-force member, then yeah, I guess you would have put some new ones up there, and you would have had too many unknowns. Maybe you could have solved it simultaneously or done some other energy methods to solve it. But finding that two-force member means that I can use this one free body diagram and solve for all three of these unknowns, which actually happen to be the same unknowns that are on this piece. There's CX and CY at this one. There's FBD there, and we already know EY. So let's solve these. I think it's probably what I would do is moments about C. That way CX, CY, the Y component of BD, and AY all do not enter that equation because they all have lines of action that intersect point C. I'll say clockwise is positive. You don't have to. You can do counterclockwise positive. So the 1700 newtons creates a counterclockwise moment. There's two of them. So this 1700 newtons. It has a moment arm of 0.2 meters. FBD is at an angle, and I'm going to use the Y component and the X component when I'm calculating these moments here. So the Y component doesn't actually create a moment about C, but the X component does. And it creates a counterclockwise moment. I'll write this down here. Minus whatever FBD is, but I only want the X component, which is 3/5. So the cosine of this angle right here. Times its moment arm of 0.4. And then this one creates a clockwise moment because if I were to push at A and be pinned at C like this, then it goes around clockwise. So plus 1700 newtons. It has a longer moment arm, 0.2, 0.2, so there's 0.4, 0.7 meters. I just didn't have enough room to run it out to the edge there, so what I'm going to do is I'll just calculate these off to the side and kind of sum them up vertically. So this is negative 1700 times 0.2 moment arm, 340. The units are Newton meters. This is negative, but it's FBD, and times 0.4 times 3 divided by 5, 0.24. The units on this coefficient are meters, right? And the newtons are held in the FBD that we don't know yet. This one is positive, 1700 times 0.7, 1190 Newton meters. So if we write our equation out, let's write it in the normal way. 0 equals negative 340 Newton meters minus FBD times 0.24 meters plus 1190 Newton meters. And we can move our FBD to the other side so it becomes positive. still has the coefficient of 0.24 meters with it, equals, and this guy is negative 340 plus 1190. So that is 850 Newton meters. And I can divide by my 0.24, and I get the force in BD is a positive, works out positive. It's a lot, 3,541.7 newtons. Kind of high compared to some of these other forces. 17, I mean, it's not terribly high, but it is high compared to some of the others. So you do want to check and make sure that all this looks correct. That looks okay. That looks right. 1190 minus 340 is the 850. Divide by 0.24 is the... All right, so I think we're good. I think the signs are good. So this means that I did draw this arrow correctly. So that's good to know. And then we can go in and CX and CY. So either do summation of forces in Y or in X. Let's do X. So in the X direction, we have 1700 to the right, 1700 to the left. So those actually cancel each other out. I'm not going to bother to write them in the equation. And I have the X component of BD. So so 0 equals FBD, but only the X component, 3 times, or 3 over 5. Plus CX equals 0. So therefore, CX is a negative FBD, which is this number here, but I only want the X component. So times 3 divided by 5, 2125. And the negative sign means that I should have drawn CX going to the left on this piece. All right. Then we need the Y direction. And we have 0 equals a negative 816.7 newtons. Whoops, sliding all over. We have a Y component for FBD, so plus FBD times the Y component, which is 4/5 of FBD, plus CY equals 0. We know what FBD is. It's that 3541.7, and we only want 4/5 of it, times 4 divided by 5. So 28, this term is 2833.4. It's positive. We need to subtract off 816.7. And we get that CY plus 2016.7 newtons equals 0. So we drew CY in the wrong direction also. So we move the 2000 over here and it becomes negative. So we've done all of our forces on this piece, and actually we've actually solved all the forces in the entire frame with this one piece here, as long as we recognize this was a two force member. All right, just for completeness though, let's draw the free body diagrams of these other pieces. So this one's actually pretty easy. I'm just going to draw it on here instead of taking a new sheet of paper for it. Yeah, we'll do it. Yeah, I'm just going to draw it down here. So there's E. Oh, no, that's D, isn't it? D. There's B. I want to draw it here because I've already assigned FBD one orientation on this piece, and I need to follow that orientation. So for me, it's easier, even if I know some things are negative over here, it's easier to draw the free body diagram of one of the pieces, and then the next piece I draw reference back to this one. I guess you could go in and, like, if this came out negative, or like CX came out negative, so you could go and erase this one and switch it over here. I just keep them and let the negative sides exist in the calculations, but not worry with them over here. So here at B and at B, I need the same magnitude, so FBD, same line of action, but I need to make this one go this way so that when I put this back together, this force and this force cancel each other out because they're reactions to each other. And once I put FBD going this way on this piece, the other end of it has to balance that. So it has to go oppose it. So up and to the right, down and to the left, so that this piece is in equilibrium. Now let's draw that top piece. I'll need a new sheet of paper for that. So it was that piece. So this is C, this is D, this is E. We have the distributed load all the way across the top, so we'll just go ahead and put that in something like this. Doesn't really matter how many arrows you draw across here. That's not the point of it. It's just showing that the arrows are all the same height and it's evenly distributed. Something like that. And it does have 2,000 newtons per meter is the value of the distributed load. At E, we found EY, we found that to be 2,016.7 newtons. We did that way back over here. At D, we have this guy. This is D, even though I kind of scribbled it up. That's D. And so on this piece, which I got this force based on it had to balance this one. I got this one based on it had to counteract this one. And so there's kind of a chain reaction here. That's why I drew this piece in the middle, just to keep it straight in my head. So at D here, I have to, when I rejoin this piece to here, this force and whatever is at D have to cancel each other out. If they don't cancel each other out, that means that there's relative motion between them and this is coming apart somehow. And we actually have a value for that, 3541.7. C, we have to do the same thing. So when I drew this one, I drew CX going to the right. Here, I'll draw it going to the left. But remember, CX is actually a negative number, so both of those arrows are backwards from what they need to be. That's what I'm talking about. For me, it's just better to keep the arrow orientation however you drew it originally, and then deal with the negative signs in any equation. So anytime you need to plug in CX, you plug in negative whatever, 2125. CY, I drew it up on this piece. So on this piece that it's connected to, it needs to go down. And again, it's actually a negative number, apparently. So both of those arrows are the wrong direction, but they're consistent. And it's more important for me that the free body diagrams are consistent, and then I get my actual directions from the equations over here. So like I said, this would have been the actual end of the problem, doing this one free body diagram. Actually, if we were over here, and the whole question is find the force in this two force member, what I would have done is moments about A to get EY, and then I would have taken the piece at the top, CDE, drawn its free body diagram, done what we did over here. Now I know EY. Then I would have done moments about C to find the force in member BD. So that would have been what I think is the most efficient path to get to the member force for BD, if that's all you're interested in. So if you're working these on an exam or something, and you are time constrained, then it does help to spend 10 to 15 seconds kind of mentally planning out how you're going to get to where you're going to get to. If you don't see a path, then the best thing probably is to find all your external reactions, the AX, AY, and EY, and then pick a piece that you know at least one thing on. So you know at least one, in this case we knew 3 different external values, and draw that free body diagram and see if you can work from there. If you ever end up in a situation where you've got too many unknowns, it probably means you missed a 2/4 member in the frame. All right. I think that's all we can do with that one. Let's do a new one. All right, so this one is going to have some new features. One new feature in particular, one that we've kind of seen before, but we haven't done a whole lot with necessarily. So here's what we're dealing with this time. So this time, let's say I don't have any like little pieces. We're just going to draw this one. Oh, that's not the good pen. All right, so here's a beam. And to this beam, we've got a couple of things connected. So we're going to have a upright somewhere in this region. We're going to have a diagonal connecting these two together, something like this. They'll be pinned, pinned, pinned. On this diagonal, in the center of it, we're going to put a pulley, maybe like this. Let's make it a little smaller, maybe like that. And around the pulley, we're going to put a rope or a cable, some kind of string of some sort. One end of it going down here, holding up some kind of weight. Then it goes around the pulley, and it comes off over here, horizontal. Oops. And I'm not going to draw it. Well, I'll do it this way so that we don't have to redraw everything. So over here, it's going to attach to a wall. And this thing is going to do a new type of fixture. So in the past, over here where the the whatever it is, the truss member or the frame beam or whatever, we've kind of had them pinned to the wall. So there was a pin there so that it would be allowed to rotate, something like this. It wouldn't be allowed to move X direction or Y direction, but it could still rotate. This one's different. Think of this one as like being embedded in the wall somehow. And so that being stuck in the wall, or maybe it's welded to the wall or bolted to the wall or whatever, we're going to call that a fixed connection. And not only does it keep the beam from moving in X or Y, but it also keeps it, if you think of this fixed, then it keeps it from moving, rotating about the wall. So this is something different, and it's going to have some different reactions on it. I'm going to draw a free body diagram, so I'm going to remove this from being connected to the wall, and we replace the wall with the forces that the wall was exerting on our beam and our rope here. So let's go ahead and assign some, this thing was lifting up something. Say that something was 50 pounds. So as long as this is a frictionless pulley, which for our doings right now, this is frictionless. Oops. We're going to give it a 1 foot diameter. but it's going to be frictionless. So as long as it's frictionless, both the rope around it and the pin at the center of it, as long as it's frictionless, then this 50 pounds just basically goes through this rope, goes around here, and you have to pull with 50 pounds in this direction. Ropes, chains, cables can only support tension unless they're really, really big. So that's how I'm going to deal with that. So originally, you know, it was connected to the wall over here. Basically what it's saying is the wall is having to pull with 50 pounds to keep this 50 pounds up over here. If there's some tension in here, not tension, if there's some friction in here, then this would be less, right? The wall wouldn't have to pull with 50 pounds of force if there's some of this 50 pounds is kind of being held in friction, kind of like a brake on this pulley. Over here, the wall, we said this was a fixed connection. So over here, not only is this having to exert some kind of, that's going to be point C. So we'll call that CX and CY. But it was also keeping this thing from rotating. So how it's doing that is it's applying a concentrated moment that we're going to call the moment at C. So this curved arrow, I don't think we've used that before in any of these lectures. So this is a concentrated moment. And we draw it with a curved arrow. It doesn't have a line of action. So it's not like an X or a Y that has a line of action that you can identify, because that's why we're drawing it as a curved thing, because it's more trying to prevent some kind of rotation or cause some kind of rotation. We need some dimensions to do anything with this though, so let's put some dimensions on here. I think I will do this. Oh wow, I drew on my ruler. Actually, let's also measure to the center of our pulley. So this will be 4 feet, 4 feet. Let's make this one 5 feet. And we need a height here, which I guess I'll put it over here. I don't really like drawing it across all this stuff, but that's what we'll do. We're going to make this one 3. I'd want to make it 4, but then this is, well, let's make it 4. Make it 4. All right. So here's our free body diagram of our frame with a pulley and a rope going over the pulley, holding up a 50-pound weight, and it's just kind of holding everything here at the wall in this fixed support. We need some letters. A, B, we already called that one C. D will be the pulley center, and E. All right, like this is a frame though. You might think it's a machine because it has a pulley, but technically the parts of it don't move. I guess this spins maybe, but the parts BE and ADE and ABC, they don't move relative to one another. So I would actually call this a frame. Always good to look for 2 force members. So ABC, even though this isn't a pin, it's still a connection point. So this cannot be a 2 force member. ADE does have 3 pins on it, so it can't be a 2 force member. BE has 2 pins and no force. This rope actually goes behind BE. It's not connected to BE. It's back behind it somewhere. So BE is a 2 force member. All right. So that might help us later. Now, we're at the stage where probably the best thing to do is find CX, CY, and this moment at C. CX and CY are actually really easy. Let's do those. Let's just look at them. So the way I drew CX, the only other X component, remember concentrated moments don't have lines of action, so they can't be in X or Y equations. The only other one is this 50 pounds. So CX should actually be 50 pounds, but go in the other direction. CY has to oppose this 50 pounds. It's the only other force in the Y direction. It is going I did draw it pointed the right way, so CY equals positive 50 pounds. The moment at C. So to do that, we need to calculate the summation of moments somewhere. We might as well use point C, since that'll eliminate CX and CY from the equation. Even though we know their values, it just is fewer things to put into the equation. So let's do summation of moments at C. We'll say clockwise is positive. Let's just deal with the moment at C first. So even though it is at C, remember why we don't include CX and CY is because their line of action goes through C. But moments, concentrated moments, don't have lines of action. So this is just in the equation. You don't multiply it times the distance. It already has units of foot-pounds or Newton meters or inch-pounds or whatever. So it is just plus or minus MC. I drew it going clockwise. I said that clockwise is positive, so it's just plus. Okay, CX and CY don't create moments about C, but these two 50 pounds do. So the moment arm, here's a vertical force, so I need this horizontal line distance, which is 5 plus 4 plus half the diameter of the pulley, which is a 1 foot diameter, so that's half a foot. So 9.5 feet to get from this line of action over to point C. And it goes around counterclockwise. So I'm seeing that I'm going to collide with that, so I'm going to drop down a little bit. Minus 50 pounds times, it had a 9.5 foot moment arm. We have to do the same thing here. We have 50 pounds. This one, we don't have an obvious, like, what's this distance? But we can figure it out with similar triangles. So if we think of triangle AEB, we have a similar triangle here, AD, whatever this point is. That's that little green one's a similar triangle. And I do know one thing, that this distance is 4 feet, and this distance is 4 feet. So this is 4, from A to B is 8. So this triangle has sides that are half the size of the similar one, the bigger similar one. So BE, the vertical distance, is 4 feet. So this little height is 2 feet. So you can go through whatever process of geometry and trig you want to figure out the height of point D here. And then I need the actual, here's the line of action. So I need the distance between this line of action and point C, which is 2 plus the radius of the pulley, which is half a foot, so 2.5. And that goes around clockwise, so plus. So here we have, we just need to calculate these numbers. 50 times 9.5. This is a negative one because it's a counterclockwise moment. Nope. Hold on. There we go. Nope. 50 times 9.5. 475. So minus 475 foot-pounds. This one is 50 times 2.5. 125 foot-pounds. It's positive because it's going around clockwise. And then MC is just positive because it is clockwise, and I said clockwise, or it's drawn clockwise. I don't actually know what orientation it has yet, but I drew it clockwise. Those have to add to 0. So negative 475 plus 125 is negative 350. I'm going to move MC to the other side of the equal sign, so it will become negative. And this is a negative 350. The units of foot-pounds. So therefore, MC equals positive, because the negative and negative, 350 foot-pounds. And this positive sign tells me that I drew this correctly. I don't want to just leave this as positive and negative though, because not everybody always draws, you know, clockwise as positive or whatever. So it's better when you get to this point on this one to write CW for clockwise or draw a clockwise arrow so that you indicate the direction right there with the number, since not everybody would have agreed. Generally people agree on, you know, X is positive when it goes to right or whatever, but sometimes it's ambiguous a little bit if you don't put the sense of the moments right there with the number. All right. So now we've got, well, I guess I could highlight these too. So we've got all of our external reactions. At this point, it's time to pick one of these pieces and draw the free body diagram for just that piece. I would probably pick ABC. Picking BE doesn't help me because I don't know any of the forces at B or at E. Picking ADE kind of helps because I at least know the forces at D from the pulley, because the pulley is attached there. So I could, if I wanted to, I could put in this 50-pound force. This is another way we could have dealt with these distances here. I could have put this 50-pound force here, right at the center of the pulley, basically taking the pulley off and thought about the pin that's holding the pulley onto member ADE. There's a hole there or a pin there that's you can think of, and the 50 pounds could be applied directly to that pin, and this 50 pounds could have been directly applied there. So we could have done that. I chose to, since we knew the diameter of the pulley, I chose to use that radius. Maybe you don't know the diameter of the pulley. If you don't, take the pulley out, look at member ADE, and you know that since it's frictionless, you can just take this force, this 50-pound force, and move it down to wherever the center of the pulley was. And you can do the same thing over here. No, it doesn't matter what angle they are. Maybe your rope's coming out this angle. You can move it down to the center of that pulley. So if you don't know anything about the size of the pulley, that's another way you can deal with these pulleys. I'm going to do ABC. Get a new sheet of paper. Oh, that's the bad one again. The mark was bothering me, so we had to flip it over. So here's ABC. So in here, I don't mind, once I start taking individual pieces, I'm okay with taking these external reactions and putting them the right way, because I'm basically not going to come back to this diagram again. So I don't mind flipping CX to go the correct orientation, but once I start drawing the individual pieces, then all those individual pieces I want to have the same system of arrows on them. So I'm going to actually put CX here going, since I calculated it to the right as negative, I'm going to go it and draw it as to the left on this piece. CY, we actually calculated positive anyway. And it was also 50 pounds. This rope just passes behind ABC, so it's not actually exerting any force. A has, both of these are two force members, so at A, all I can do is AX and AY. At B, I did decide this was a two force member, so here I can just draw FBE, and I can either, I know it's line of action, and I just have to decide, is it pushing down or pushing up on B on this piece. So I'll just pick one. We'll do that one and call it FBE. And then we have a couple of dimensions. Basically, we have 8 and 5, right? from, they're off the screen, but there they are. 8 from A to B, and B to C is 5. So let's put those on here. This is 8 feet, and that's 5 feet. Okay. Oh, we left off our new thing, didn't we? We left off our moment at C. So we calculated that as 350 clockwise foot-pounds. So I'm going to put 350 foot-pounds clockwise right there at C. All right. We're getting close. The part that we have 3 unknowns, right? If you had not seen member BE as a 2-force member, you would have BX and BY and 4 unknowns, and you'd kind of be stuck. You could get some of them, but not the X components. You could get the 2 Y components, but not the X components. But since we recognized it as a 2-force member, then we only have 1, 2, 3 unknowns, and we can solve for all of them. What we should do is, a lot of times I go and I do moments about C, where that pin was. But in this case, I have 2 unknowns over here at X and at A. AX and AY are both unknown. So I'm going to do moments about A to eliminate these 2 from the equation I'm writing. All right, so I've got FBE. It's a vertical line of action, so I need a horizontal distance, which is an 8-foot moment arm. It's going around clockwise. And I say clockwise was positive. Okay, I've got the 50 foot-pounds here doesn't create a moment about A, neither does AY or AX. This 50 pounds creates a counterclockwise moment, right? If I think about pinned at A and push up here, then my body goes around counterclockwise. So that would be negative, according to my equation, with a 13-foot moment arm, 8 plus 5. The 350, even though it's not at A, I still only include it as plus or minus. It is clockwise. I said clockwise is positive, so I just put plus 350 foot-pounds. You don't multiply it times the 13 feet. If I did, I'd have units of foot squared pounds, which is not a moment. Now I've got 1 unknown. So we can move FBE over to the other side. So it's negative FBE times 8 feet equals this thing, which is, this one is negative 50 times 13. So this term is negative 650 foot-pounds plus 350 foot-pounds. So this whole term is negative 300 foot-pounds. FBE was negative when I moved it over, so FBE equals positive 300 divided by 8, 37.5 pounds. So I did choose the right orientation for FBE. At that point, I would go in and write summation of forces in X direction. AX is 50 pounds. The only other force there's this one. The moment doesn't have a line of action to contribute to X or Y. In the Y direction, I have AY minus FBE plus 50 pounds. This 50 pounds. FBE is 37.5. So I'm going to move AY to the other side. Negative AY equals negative 37.5 pounds plus 50 pounds. Therefore, AY is equal to, this term comes out positive, but AY is negative, so it's a negative one. 50 minus 37.5, 12.5. And now we've got all of our forces on member ABC. So there's BE there's AX, and there's AY. And we've actually, and this is another one of those where we've actually solved the entire thing, because the other, oh, that's not it. That's the, here it is. The other one, remember ADE, we already know the reactions at A, we just found them. The reaction at E is given through the force in BE. And at D, if we really want to deal with it, it's just, we can put the 50 pounds at D from the rope if we want to. Or we can draw the pulley and draw the ropes and put the 50 pounds on the ropes, whichever way you want to do it. So this is another one of those where one piece solves the entire frame. All right. I think that's probably a good stopping point for this one. We'll do a little bit more on frames and machines next time on Monday. And then we're beginning to get into beams. So we'll look at frames and machines, but now we'll look at, all right, this is a beam. And this beam with these forces on it is, it's bending and flexing and all these different shapes. And we want to know what that looks like and how much flexing is going on, what kind of flexural stress is there. That's not quite the same as axial stress that we did earlier. So we're kind of going to transition into that idea. But we'll do that on Monday, and see you on Monday. I think we're good for today.